tangential. And the key word tangential. Now tangential comes from the word tangent, and tangent comes from something that touches in only one spot and it's perpendicular. So this velocity right here of the object right here, if we were to cut the string, it would fly off in that direction. At this point right here, if all of a sudden I were to cut the string, it would fly off in this direction. So you can see that it's perpendicular to the circle and perfectly straight and only touches in one spot. This is what we call our tangential velocity, and we use the little sub t to tell us that it's a tangential velocity. This tangential velocity is dependent upon the radius of the circular path. So yesterday when we did our lab, the radius was the distance from the stopper to the center here. If that radius increased or decreased, that is what changed the velocity. So this is our tangential velocity. If I increased it, I have to spin it faster to keep it going. And so you can see that the radius of the circular path is what's going to be important to keep that velocity or that tangential velocity constant. Okay, so now tangential velocity back from kinematics is just a change in distance over the change in time. So the distance that we're going to be talking about is the distance that the object moves from here to here. Now one full rotation is the circumference of the circle. So later on we're going to talk about this, but this is just S, it's just the arc length that that object has moved. Okay, well, we talked about tangential velocity, but now what about acceleration? So we said that uniform acceleration is constant speed, which means that that acceleration would have to be 0 if the tangential velocity is constant. But we do have acceleration when we go around a circular path. Well, how do we get that? Well, we have to remember that velocity is a vector, and a velocity has a magnitude and a direction. Okay, so we're saying right here that if it's constant speed, then this magnitude doesn't change. But in this case, you can see here that the direction of the velocity has changed. If the first time it's going in this direction, over here it's going in that direction. So we have a change in direction of the velocity. And this change in direction is what we're going to be talking about. It's the acceleration based on the change in direction of the velocity, not based on the change in the magnitude. So we're going to talk about the change in direction over a change in time. Well, this is a special type of acceleration. So how do we find out what the change of direction is? Well, remember when we find out the change of velocity, it's just change in velocity is just our final velocity minus our initial velocity. Well, how do we do that? Well, this is just tip to tail method. So we're going to say V2 plus a negative V1, okay, which is really V2 minus V1. And what we're going to do is we're going to do tip to tail. Now, a negative V1 is just the V1 and you flip direction. So if V2 looks like this, and negative V1 is just the same as V1 but flipped, now we're going to do tip to tail. So we're going to start with V2, and then what we're going to do is we're going to do a V1. So here's V2, and then V1, and then what we're going to find here is this is going to be our change in velocity, which is our V2 minus V1. So we know that from here to here we have an acceleration that's pointing in this direction. Excuse me, the direction would be right here. You can see here. Okay, and we're going to talk about, this is the acceleration that we're going to be talking about. The change in velocity is the acceleration that we're talking about. Well, it's a special type of acceleration, and it only happens when you're going around a curved pathway, because if you're going straight, you don't have the change in direction. This is what we call centripetal acceleration. The word centripetal is a Greek word that comes from center seeking. So what's happening here is going to be an acceleration that looks towards the center, center seeking. Okay, so it's always going to be pointing towards the center of the circle. So first let's talk about the magnitude, because acceleration is a vector. It has a magnitude and a direction. Well, the magnitude comes from this equation. The acceleration centripetal, and we use that little c telling us it's centripetal, just like we use the acceleration in the x direction or the acceleration in the y. Well, now we have an acceleration in the center direction. This equation is going to be the tangential velocity squared over the radius. And we know that from the lab that we did yesterday, because the acceleration changed when we changed the radius, and the acceleration changed when we changed the speed. And we talked about that in the synopsis that we wrote. Well, the direction of this is always towards the center of a circular path. So let's talk about a Ferris wheel, okay? And you're at the top right here in this bucket of the Ferris wheel, and you're hanging down, okay? And the Ferris wheel is going to be turning this way. Well, you have a tangential velocity that's going straight at this point. Well, the acceleration is always towards the center of the circle. Well, now what happens when you're down here? Okay, so you're still on your Ferris wheel, but now you're at the bottom. Well, if you look here, now we're going to be moving here. Your tangential velocity is going that way because this is going around in a circle. Well, your acceleration is always towards the center. So now our centripetal acceleration will point upward. Okay, and we'll get in more detail later on. The units that we use for acceleration are the same as any other acceleration, meters per second squared. Okay, so remember the magnitude is the tangential velocity squared over the radius. The direction is always towards the center of that pathway, and the units are meters per second squared. So let's try a problem that uses centripetal acceleration. Okay, so we're first going to be talking about a washing machine tub. So a cylindrical tub of a washing machine has a radius of 34 centimeters. During the spin cycle, the walls of the cylinder rotate with a tangential speed of 5.5 meters per second. Calculate the centripetal acceleration of the clothes spinning against the tub. So we're going to be talking about if this was a top-loading washer. Okay, here's the tub, and you have something, and this is going to spin around really, really fast, and what happens is the clothes spread out to the outside radius of that tub, and what we're finding is what is the acceleration. Well, we know from here that it has a radius of 34 centimeters, but we need to be in meters, so we're going to convert that 34 centimeters to 0.34 meters. We also know that it has a speed, a tangential speed of 5.5, and we're looking for centripetal acceleration. So we're going to start with our equation. Our centripetal acceleration is our tangential velocity squared over the radius. We just plug the numbers in. Don't forget to square it. And then we're going to divide it by that, and we end up with the centripetal acceleration of 89 meters per second squared. And remember, the direction is always towards the center. Okay, let's try another one now. Okay, a test car is moving at a constant speed around a circular track. If the car is 48.2 meters from the track center and has a centripetal acceleration of 8.05 meters per second squared, what is the tangential speed? Well, we're going to start here. We know that it has a radius of 48.2 meters from the track center, and the centripetal acceleration is 8.05 meters per second squared. What is the car's tangential speed? Okay, so we're going to use our equation. Centripetal acceleration is v tangential squared over r. Then what we're going to do is we're solving for v tangential. So we're going to cross multiply. Centripetal acceleration times r is vt squared, but we don't want it squared. We want to solve for just vt, so we take the square root of both sides. Plug in our equations, 8.05 times 48.2, and then take the square root of it, and we end up with 19.7 meters per second, and that is the tangential velocity. Okay, so what we're talking about here is a car moving down a circular track. An example that you can see here is if you're driving on I-95, okay, so here's I-95, and you're going to exit at, I think Fisk Boulevard is a good example, but Fisk Boulevard, the exit takes you around a circle. Okay, so if you're exiting here, you have a circular path with a radius r. Well, what happens? There's always a sign right there, and that sign tells you to slow your speed down. The reason why is because your centripetal acceleration, even if you're at a constant speed, is going to make you feel like you're going much faster. And you guys know what I'm talking about. As you exit that highway, if you don't step on the brake, you're going to end up going so fast, you'll end up going straight this way. So to be able to keep along that path, you have to slow the velocity down. Another way that you could do it is increase the radius. So if this radius were large enough, that curve, you wouldn't have to slow the velocity down. But there's two factors that affect the acceleration. One is the velocity, the other is that radius that you're going to be turning on. So an example on a highway has much larger radius than, say you're driving down your road and you need to turn left into your street. Okay, so this might be Murrell Road and you're driving down here and you have to make a right-hand turn. Well, right here, this is a much shorter radius than something like this. So that's why you're going much slower on Murrell Road. They have a shorter radius of this turn. On a higher speed over here, they have to have a much larger radius. Okay, so that's an example of a test car driving around a circle. Okay, we'll recall from Newton's second law. Newton's second law tells us that all the forces have to be equal to mass times acceleration. So what what creates the acceleration as a force? So now we can say that there is a centripetal force. Okay, so we've been talking just about force. We have one more force to add, centripetal force, that causes an object to accelerate along a circular path. So what causes centripetal acceleration? It's a centripetal force. Now remember that centripetal acceleration is equal to tangential velocity squared over r. Therefore, we can keep this going and we can say mass times vt squared over the radius. This is what you feel when you're going around the curve, exiting a highway. This is what you feel when you're going on the loop-de-loop of a roller coaster or the very top of a roller coaster. That is the force that you're going to be feeling. This is also the force that when we were spinning that tube around, that's what you felt in your hand. You could feel that centripetal force. Let's try an example with centripetal force. Okay, we have a pilot that's flying around a small plane at 56.6 meters per second. This is our velocity in a circular path with a radius of 188.5 meters. The mass of the plane is 1,110 kilograms. And what is the centripetal force needed to keep that plane flying in a circular path? So that's going to be that force. If you can remember exiting off the highway, you have to force yourself to keep going in a circular path. Otherwise, your car is going to want to go straight. And so we have a plane that's flying, and this is an aerial view, but it's flying around. If you can kind of picture, here's your plane, and that's your tail, and here's the front, and this is your tangential velocity of this airplane. For it to keep going in this circular path, that pilot has to exert some sort of force to create that circular path, and that's what we're finding. So our given is our tangential velocity of 56.6 meters per second, and that's given right here. The radius is 188.5 meters, and the mass of the plane is 1,110 kilograms. We're looking for FC. Well, we know FC is mass times acceleration. The acceleration is the centripetal acceleration. So FC is mass times V tangential squared over R. Then all we have to do is just plug in the numbers. The force needed, this pilot needs to create a force of 1.89 times 10 to the 4th newtons to keep that plane going in a circular path. Otherwise, the plane is going to want to follow that tangential velocity and go straight. Okay, and remember, force is in newtons, and we have newtons here. Okay, so that's the last of the slide today. Tomorrow we're going to do some of these problems in class. Don't forget to do the assignment that's on Edline, and we'll see you tomorrow in class.